So we will determine what is the rate law. This is the rate law expression. So then this is the rate law expression. This was as per the law of mass action. So what is the rate law expression we can define here? A rate law expression. I will define rate law expression. Expression. It is equal to, we can define rate law expression. It's a mathematical expression. It's a mathematical expression which determines or which denotes the rate of reaction in terms of the mole concentration of reactants with each term, each concentration term raised to the power which you must remember, which may or may not be equal to stoichiometric coefficients. Stoichiometric coefficients these are determined experimentally. An example, I will explain it here. For example, these coefficients may be positive. Generally, they are positive numbers, whole numbers. They are positive. They can be negative. These concentration powers जो होते हैं, they can be generally they are positive. They can be negative also. They can be zero also. For example, I will write here a general equation. H2O2, decomposition of hydrogen peroxide gives oxygen in presence of iodide ions. Now, this here it is the catalyst. In this case, rate is proportional as per experimental. This rate of law expression is equal to, in case of this fact, is K concentration of H2O2 but not raised to the power of its stoichiometric coefficient into I negative ions. That means here concentration of the catalyst, homogeneous catalyst, this I negative ion is taken into consideration. So this is the rate law expression. Or we can write for this general equation, I will write it here. If it is m times m1a plus m2b plus gives products. Here C is the catalyst. I will write the rate law expression. I will write here is equal to K concentration A raised power alpha, concentration B raised power beta, and concentration of C raised power gamma. That means, however, the C is your catalyst. So sometimes this rate also depends upon the concentration, as you have seen, concentration of the catalyst, as you have seen in the decomposition of hydrogen peroxide. So this is the rate law expression. For example, I will write an equation here. You have written. First, I will write it. For example, nitrogen pentoxide gives NO2 plus O2. This is the reaction. Now, you will write as per the law. I will show first law of mass action. As per the law of mass action, rate is proportional to the rate is equal to K concentration of N2O5 raised power 2, because stoichiometric coefficient is 2. But actually, as what has been determined experimentally, so rate is equal to K N2O5, not raised power 2. So this is the rate law expression. This is the rate law expression. That means law of mass action is theoretical. The equation of law of mass action is theoretical, as given by the law. And this rate law expression is based on the experimental evidence. We have to carry out the experiments to find the actual dependence of the rate, actual dependence of the concentration terms on which the rate depends. For example, I will write in here equation. This is the equation. Twice NO2 gives twice NO plus O2. If I will write here a law of mass action, as per this rate expression, for this is rate is equal to K concentration of NO2 raised power 2. That means I have shown sometimes it may be equal to the stoichiometric coefficients and sometimes it is not equal to the stoichiometric coefficients. Here I will explain this equation. I will write the mechanism of this reaction. For example, I will write it as NO2 gives NO plus O. This is the reaction. This is the solo step. Now I will write NO. Again, second NO2 plus O gives NO plus O2. If you add this, this is the first step. So I will add this equation. It will give twice NO2 gives twice NO plus O2. Rate, since you know rate depends upon the soloist step, so rate will be equal to NO2 K NO2. Now this first keep it in mind. Now I will write second mechanism for this reaction. I will write the second mechanism. For example, NO2. This is the first mechanism. Second mechanism I will write here for the reaction NO2 plus NO2 gives NO3 plus NO. This is the reaction. Now NO3 gives NO plus O2. Now this is the first, this is the solo step, that is rate determining step. This is the fast step. So rate depends upon the solo step. We can write the rate for this reaction is equal to K. Rate is equal in this reaction, in this mechanism, rate is equal to K NO2 raised power 2. Now here, in this first mechanism, we have seen that rate is proportional to K NO2. Here it is NO2 raised power 2. Now experimental evidences. Experimentally, this mechanism is agreed and this mechanism is not agreed. The mechanism which is agreed experimentally is actual, gives the actual rate of the rate law expression. And the mechanism which does not agree with the experimental evidences will not give the rate of this rate law expression. That means for the rate law expression we have to describe, then we have to carry the experiments to find the actual concentration terms on which the rate depends. Here I have shown the two mechanisms. In the first mechanism, here I have shown that rate depends upon the concentration term of NO2, and here I have shown the rate concentration term of NO2 whole raised power 2. But first mechanism and second mechanism. First mechanism does not agree with the experimental values, experimental evidences, and second agrees with the experimental evidences. So rate law expression for this is rate is proportional to K NO2 raised power 2. So we came to conclusion that rate law expression is a mathematical expression. It's in which shows that which denotes the rate of reaction in terms of the molar concentration of reactants with each raised to the power of the stoichiometric raised to the power, which are determined experimentally. they may or may not be equal to the stoichiometric coefficients. Thank you. This was the rate law expression.